Good morning. This is Engineering Mechanics. Once again, we're using the fifth edition, the Hibbler text. And today we're going to begin working in chapter 5. And our objectives here is to determine the forces and the members of a truss using two methods: method of joints, and later on, method of sections. So what is a truss? It's a structure that is composed of slender members joined together at their endpoints. So you see truss commonly on bridges and say cranes, etc. And they look a simplified one. And these are the members. And typically they're joined at the ends by pins. So some assumptions. All loadings are applied at the joints. And members are held together by smooth pins. So therefore, each truss acts as a two-force member, which means the forces act at each end of the truss. For example, if we take a member and there's a pulling force at the end, then we say that member, we'll say pulling force which means it's tending to elongate it, then this member is under tension. Likewise, if the same member is experiencing a compressing force, which is trying to compress it, so the opposite of elongate, trying to shorten the member, we'll say tending to shorten the member, then this member is under compression. So tension versus compression. And we're represented by T and C. Because in our problem solving coming up, a lot of the problems will ask us to, once we solve with the forces that are in the members, to state whether the member is in tension or compression. So the forces acting through the members are tending to pull or elongate the member is tension. If it's tending to compress or shorten the member, then it's under compression. So our first, say, truss problem solving method, and this is method of joints. This is assumes or based on the assumption for statics, that is, just to keep hitting that point, that the entire truss is in equilibrium. Therefore, each of its joints must be in equilibrium as well. So if we drew the free body diagram of each joint, we can use the force equilibrium equations, which we know is sum of forces in the x direction equals 0 and the sum of forces in the y direction equals 0. And we use these two equations to determine the member forces acting on each joint. So if we look on page 226 of the textbook, and this is figure 5-7, they give you example of a simple truss. It's pinned at A. So rocker at C. And B is a pin, smooth pin. This is where the two members, member AB and member BC, come together at this joint. We'll say smooth pin at joint B. And joint B is connected from members, and we usually state the members based on the other joints that come together. For example, the pin at A, rocker at C, and the smooth pin at B. Then at joint B, members AB. So joint B is constructed from members AB and member B, C. And you can write it either way, member AB or member BA or member BC or member CB. You can rearrange the letter whatever is most clear. But as we see, this is member AB, this is member BC. All right. So this is joint B. And they gave us a pulling force at joint B of 500 newtons. So then if we do a free body diagram of joint B, so we have the 500 Newton force that's given. And its sense of that force vector is to the positive x direction or to the right. And for equilibrium, our forces in the x direction must balance out to give 0, and our forces in the y direction must balance out to equal 0. So with given the 500 Newton, how do we model the forces in members BC and members AB? Well, the 500 Newton force goes to the right, so to balance that out, the x component of our FBC member force, it has to go to the left to balance it out. Well, then if it's going to the left or in the negative x direction, then the orientation of the y component is pointing up vertically. Well, that means then the force AB has to be orientated down, the sense of it, that is, to balance out the y component of BC. So you see now these forces are all balanced out. 500 Newton force to the right, the x component of member force FBC has to go to the left. And since it's going to the left to balance out the 500 Newton force, then the y component of force BC is orientated in the positive y direction or up vertically. So then the FBA, which is purely a y direction force, has to be oriented down in a negative y direction. So a technique when we're doing these truss problem solving is to always, we'll say, problem solving strategy, method of joints. Always start at a joint having at least one known force and at most two unknown forces. All right, so let's take a quick look at the problem to gauge our understanding and begin working. Let's look at example 5.1. This is page 228 in text. The problem states or asks us to determine the force in each member of the truss and indicate whether the members are in tension or compression. So this is a simple truss. We're given a 500 Newton force at joint B. is a pin at A. And there's a rocker at C. So if we begin at joint B, and do our individual free body diagram there, there is one known 500 Newton force at that joint, and there's two unknowns. We have the FBC, which is unknown, and we have the FAB, which is unknown. So we have one known, two unknowns. And our rule is always start at a joint having at least one known force and at most two unknown. So we can work here. So we start at joint B using our equilibrium equations. In the x direction, 500 newtons is in the positive, and we can subtract the, this angle here is, this is 45 degrees, and this angle here is 45 degrees. Okay, so we can set up our forces to determine the unknowns one at a time using our equilibrium equations. So the 500 Newton force is in the positive x direction, minus FBC, which has vertical and horizontal components. We want the horizontal component here, which would be sine of that angle, and equals 0. Solve for the unknown. FBC is 707.1 newtons. Now, this FBC, but the problem asks us to state whether the members are in tension or compression. FBC is in compression. Let's take a look at the sum of the forces in the y direction. So we now know FBC is 707 newtons. So we want the y component of that force, which would be cosine of 45 degrees. That'd be 707.1 newtons. Times cosine of 45 degrees minus FAB. Solving for FAB, FAB equals to 500 newtons. And now this force is pulling from the joint, so this is in tension. So we calculated, so there's three members in this simple truss, AB, BC, and AC. And we've calculated the forces in two of those members. So the only one left now is member AC. So if we then go to joint C and construct our free body diagram, the rocker only has a Y component to it. We know what BC is as 707.1 newtons. And since the rocker is a positive Y direction, then BC must be coming down to balance it out. And we know FBC, as we already calculated, 707.1 newtons. And therefore, FAC must be going to the left to balance out the positive x direction component of FBC. Remember, it all has to be in equilibrium. So the sum of it in each direction must equal 0. So then, if we take our forces in the x direction equals 0, we have our FBC, which is 707.1 times cosine of 45 degrees minus FAC equals 0. FAC is 500 newtons and is pulling away from joint C, so that's in tension. And those are the forces in the members. Let's take a look at another one. Let's take a look at example 5.3. It's page 230 in text. Here, they want us to determine the force in each member of this truss, indicate whether the members are in tension or compression. So let's draw our okay. This is joint C. This is a pin. We have at joint D, a 600 Newton force here. We have a 400 Newton force at joint B. A is a rocker. This is 3 meters. And that's 3 meters. That's 4 meters. Okay. So with A being a rocker, we have a AY component here. So there's 3 unknowns at joint A, no knowns. There's 1 unknown at joint B, the 400 Newton force. Yet there's 3 unknowns here, the force in member AB, the force in member BD, and the force in member BC. So 1 known, 3 unknowns. Remember, we need 1 known and at most 2 unknowns, so we can't solve that. We can't solve at joint A. Joint D has 1 known, the 600 Newton force, but once again 3 unknowns, the force in members DC, BD, and AD. So we can't solve that joint. And then at joint C, which is a pin, we have the CX and CY components of the support reaction pin, and the forces in members BC and CD. So 4 unknowns there. So our rule is 1 known and 2 unknowns, but none of these joints fit. So how do we solve this problem? Well, if we start with an overall free body diagram of the entire truss, let's say including support reactions, to break down some of those unknowns. So let's redraw a free body diagram now, considering that. So A is a rocker, so it's just a Y component. C is a pin. So to balance out the 600, we have to have our x component go to the left. So this is our overall free body diagram with the external forces and the support reactions. Let's go to a clean page. We'll use this picture. Okay, so let's get to work. If we remember, this is our overall free body diagram. Chapter 4 work, which is what we're doing now. So if we take out forces in the x direction, then we have the 600 Newton force, which is in positive x direction, minus Cx equals 0. Cx equals to 600 newtons. If we take some of the moments about point C, we can eliminate Cx and Cy because they cause no rotation about point C as they go through point C. So then we have the 600 Newton force times the perpendicular distance, which is 4 meters. That causes a counterclockwise about point C. We have the 400 Newton force times the perpendicular distance, which is 3 meters. Counterclockwise, so positive. AY causes a clockwise about point C, so that's negative. Perpendicular distance here is 6 meters. Solving for AY, you get AY is 600 newtons. Leaving you one unknown, which is CY. So if we do our sum of our forces in the Y direction, we have our AY, 600 newtons, minus the 400 newtons, minus CY equals 0. Therefore, CY is 200 newtons. So now we have calculated some of the unknowns. We can begin to figure out the forces in the members by doing our joint work. Okay. So we know our CY, we calculated, is 200 newtons. Our CX, we said, is 600 newtons. And our AY is 600 newtons. So now, if we start at joint A, we have our AY and we have our force in the member FAB. The sense has to come down to balance out the vertical component AY, which then means our force in member AD, which is horizontal, has to go to the right in the positive x direction. So two unknowns and now one known we can solve. So we take out some of our forces in the x direction, I should say in the y direction. Put it that way first. We have 600 newtons, which is the AY, minus FAB. But what is the vertical component of FAB? Well, we notice in the problem, this distance here is 3 meters, and this is 3 meters, and this height is 4 meters. Well, then that slope triangle is a 3, 4, it has to be 5. So this is the right triangle. So then FAB, the vertical component, would be 4/5. Solve for that. FAB is 750 newtons. FAB is pushing into joint A, so that's compression. Now our sum of the forces in the x direction, we have FAD minus FAB, which we now know is 750 newtons, times the x component of FAB, which is 3/5. FAD is 450 newtons and is pulling, so it's in tension. Let's go to the next joint. If we go to joint D now, and draw a free body diagram at this joint, we have force in member FDC. So we have the 600 Newton force. We have the force in member FDC. And we have the force in member FDB or FBD. And we have FAD, which we calculated in the previous joint to be, this is FAD, which we now know is 450 newtons. So we have two knowns and two unknowns. We can solve it. And once again, we know this angle here, due to the dimensions, is a 3, 4, 5 triangle. That's the slope triangle. So then if we start working here, we have some of the forces in the x direction. We have our 600 Newton force minus our 450 Newton force minus our FBD, and x component is 3/5. Solving for FBD, (250 newtons). Then the sum of our forces in the y direction, we know our FBD now is 250 newtons times the y component, which is 4/5, minus our FDC equals 0. FDC, 200 newtons. FBD is pulling from joint D, so that's in tension. FDC is in compression. So the last member, force in the member we have to determine is FBC. So if we take a look at joint C, we know that C had a CY and CX, which we calculated, along with forces in members BC and CD. So we have CY, which we know is 200 newtons. We have our CX, which we determined to be 600 newtons. We have our oh, sorry, I got that backwards. This is my FCD. We have our CY, which we said is coming down, which is 200 newtons. And we have our FCB, and we calculate our FCD in the previous joint to be 200 newtons. So you see that very nicely now that our CY, which we calculated to be 200 newtons in our support reaction, and the FCD we calculated at the previous joint D are both 200 newtons. They're both in the Y direction, and they cancel out. So this is further proof that our assumptions and our work we're doing is correct. So to calculate the last member force, FBC, sum of forces in the X direction, we have FBC minus 600 newtons equals 0. So FBC is 600 newtons. So we have solved for the force in every member of this truss diagram. So let's look at some problems from the text. Start with problem 5.1. On page 237. Here is asking us to determine the force in each member of this truss and state if the members are in tension or compression. So let's start with it. See, P1 is given as 20 kilonewtons. We have P2 given as 10 kilonewtons, which is joint D. A is a pin. B is a pin as well. So remember our rule, start at a joint with one known, at least one known, at most two unknowns. This is our rule. So joint C has one known, P1, which is 20 kilonewtons, and two unknowns, members CD and members CB. So we start with a free body diagram of joint C. we have our 20 kilonewton P1 force coming down, which means that FCD must be orientated up in the positive Y direction. And there's only one force in the X direction, FCB. So if I take some of my forces in the X direction, we have FCB equals 0 newtons. In the Y direction, I have FCD minus 20 newtons. I'm sorry, kilonewtons, not newtons. Equals 0. FCD is 20 kilonewtons. And since FCD is pushing into that joint, it is in compression. So we've calculated the forces in members CB and CD, leaving us two left members, the forces in members DB and DA. So then if I go to joint D and do its free body diagram, we have the P2, which was given as 10 kilonewtons, horizontal direction. We have the FDA unknown. We have our FDB and our FCD, which we now know is 20 kilonewtons. So we have two knowns here, the 10 kilonewton and the 20 kilonewton, and two unknowns, FDB, FDA. So if I start in the Y direction, I have my, oh, and one more thing, the angle here, this height is given as 1.5 meters. This length is given as 2 meters. Well, if you double those, 1.5 times 2 is 3, 2 times 2 is 4, then this becomes a 3, 4, 5 slope triangle ratio. So if I take the sum of my forces at joint D in the Y direction, I have my FBD times 3 over 5, 3 over 5, 3/5, minus 20 kilonewtons equals 0. So FBD is 33.3 kilonewtons, and it's pulling, so it's in tension. If I take my forces in the X direction, we now know FDB, so there's one unknown left, FAD. You have your 10 kilonewton plus your 33.3 times 4/5 minus your FAD. Solving for FAD, you get 36.7 kilonewtons, and it's in compression. So we solve for every member force. Let's do another problem. Let's look at the very next one. 5.2. Same page. This is a pin at B. This is a pin at A. P2 is given as 30 kilonewtons. P1 is given as 45 kilonewtons. Joint C, joint D. This is 2 meters. This is 1.5 meters. So once again, if we start at joint C and draw a free body diagram, we have a 45 kilonewton force coming down. We have CB, the force in member CB, and you have FCD. So we have one known, two unknowns. We can solve. One known, two unknowns. That's our rule. So then if we solve this problem out, sum of our forces in the x direction equals 0. FCB equals 0. Sum of forces in the y direction, we have FCD minus 45 kilonewtons. FCD is equal to 45 kilonewtons, and that is in compression. So if I then work to joint D, we have 30 kilonewton force. We have our FAD. We have our FCD, which we now know is 45 kilonewtons from our analysis at joint C. And we have the FDB. And once again, this is a 3-4-5 slope triangle ratio. So we take the sum of our forces in the y direction. You have your FDB times 3/5, which is the vertical component of FDB, minus the 45 kilonewtons. You have FDB is 75 kilonewtons, and it's pulling from the joint D, so it's in tension. Take the sum of our forces in the x direction. We now know FDB, so it's 75 kilonewtons times 4/5, which is the x component, plus the 30 kilonewtons, P2, minus FAD, and FAD gives you 90 kilonewtons. Take a look at another problem. 5-3. Once again, they want us to determine the force in each member of this truss and state if the members are in tension or compression. F is a pin. E is a roller. Joint D, joint B, joint C, joint A, and we're given a 130 pound force with the slope triangle. Okay. So if I start at joint A, there's one known, the 130 pound force, and two unknowns, the force in members AB and AC. So we can get to work. Before we get that, let's get this picture saved. So fresh page. What we can do. Okay, so let's start at joint A. So a free body diagram here. We have the 130 pound force. And of course, for X and Y axis, this is our orientation. So we have the slope triangle 5, 12, 13. We have FAC. And we have FAB. Two unknowns, one known. So if I take some of my forces in the Y direction first, you have, one more thing. If you look at the triangle, this is 4, 3. So then this is a 3, 4, 5 slope triangle here. So if I take the sum of my forces in the Y direction, 4 feet, 3 feet. In the Y direction, we have FAC times 4 over 5 minus the 130 pound force times 12 over 13. So FAC is 150 pound force and it's pushing into joint A, so it's compression. Taking some of the forces in the X direction, we have FAB minus FAC, which we now know, so let's put that there, which is 150 pound force, times the 3 over 5 minus the 130 pound force times 5/13. Solve for FAB. You get FAB is 140 pound force and it's pulling, so it's in tension. So we go to so now we know that, so we go to joint B. We know the force in member AB, which is calculated at, is 140 pound force. So that leaves us two unknowns at joint B. Let's construct it. don't know FBC, and we don't know FBD, but we do know FAB, which we said is 140-pound force. So I take the sum of my forces in the y direction. We have FBC equals 0-pound force. If I take the sum of my forces in the x direction, we have FBD minus 140-pound force. You get FBD is equal to 140-pound force. And this is in tension, it's pulling. Let's go to a clean page. So now if we go to joint C, we know FBC now, and we know FAC. So we know FBC, we know FAC. It leaves us two unknowns, which would be FCD and FCE. So two knowns, two unknowns. So joint C, FCD, which we do not know. We have FAC, which we said is 150 pounds force. We said FBC is 0. So AC, BC, CD, and our last unknown, which is FCE. So if we take our sum of our forces in the y direction, and remember this here is a 3, 4, 5 as well. So we have our FCD times the 4/5 minus 0, which is FBC, minus FAC, which we know already now as 150-pound force, times 4/5 equals 0. Solve for FCD. We get 150-pound force, and it's pulling, so it's in tension. Taking the sum of the forces in the x direction, we now know FCD, so which is 150-pound force. So it's 150-pound force times 3/5 minus FCE, our last unknown at this joint, plus FAC, which we said is 150, times 3/5 equals 0. FCE is 180 and FCE is in compression. So now if we go to joint D, so you see we're working from joint to joint, joint to joint. We have FDF, which is an unknown. We have FDE, we know FCD is 150 pound force. We just calculated that. And we know from before that FBD is 140 pound force. So we have an unknown member force FDF, unknown member force FDE. We know FCD, and we know FBD. So two knowns, two unknowns. So we take the sum of our forces in the in the y direction. We have FDE minus FCD, which is 150 pound force, times the vertical component, which is 4/5. We get FDE equals 120 pound force, and that is in compression. Taking the sum of our forces in the x direction, we have our other unknown, FDF minus FBD, which is 140 pound force, minus FCD, which is 150 pound force, times its x component, which is 3/5, equal to 0. FDF is 230 pound force and is pulling, so is in tension. So if we now work at joint E, the roller at E is a vertical component of that support reaction. We know we have FCE, which we calculated previously to be 180 pounds force. FEF is an unknown. This is a 3-4-5 slope triangle. And then we have FDE coming down, which we calculated to be 120 pound force. So we have FDE, 120 pound force. At joint E, we have FCE, which you said is 180. We have the roller support reaction, which is EY, the Y component, and we have FEF. So if I take sum of the forces in the x direction equals 0, I have my 180-pound force, FCE, minus the FEF times the 3/5 slope triangle ratio. Solving for FEF, you get 300-pound force, and this is in compression. And that was the last member. So we solved all of the member forces of this stress diagram. Take a look at another problem. Let's look at 5.5, page 237. Here wants us once again to determine the force in each member of this truss and state if the members are in tension or compression. Theta equals 0. So then the roller at C, this is a roller. It is horizontal because that angle theta is 0. All right. So then that means, let's say Y component force here. Let me do it this way. See Y. That support reaction roller. Should I say Y component? We have this is joint B. This is a 4 kilonewton force. At joint D, we have a 3 kilonewton force. A is a pin. So we have a AX and an AY. And I believe I have everything. This distance here is 2 meters. And this distance here is 1.5 meters. Okay. So if I was to start at joint A, there's two unknowns with the support reaction, AX, AY, and there's the unknown in the members, AD and AB. So there's 4 unknowns at A and no knowns. So we can't start at that joint. At joint B, we have one known, the 4 kilonewton force, but we have 3 unknown member forces, members force AB, BD, and BC. So we have 3 unknowns, 1 known. Remember our rule, at most 2 unknowns with 1 known. At joint D, we have the 1 known, 3 kilonewton, but 3 unknowns, AD, BD, DC. And at C, we have 3 unknowns, the roller CY and the members CD and BC. So when we come to this situation, before we can do our joint analysis, we have to do an overall free body diagram of the structure, taking into account the support reactions. So going back to our chapter 4 tools, if I take some of the moments about point A, which eliminates AX and AY, we know CY causes a counterclockwise positive. Perpendicular distance is 4 meters. The 3 kilonewton force at D is clockwise, negative. Perpendicular distance is 1.5 meters. We have a 4 kilonewton clockwise rotation causing force was separated by a perpendicular distance of 2 meters. Solve for this. You get Cy is equal to 3.125 kilonewtons. So now I do my sum of my forces in the x direction. You have 3 kilonewtons minus AX equals 0. AX equals 3 kilonewtons. I do the sum of my forces in the y direction. You have a y minus your 4 kilonewtons plus your 3.125 Cy force. You get a y 0.875 kilonewtons. Okay, so I know my support reactions now. So now going into the method of joints. If I start at joint C, we now know Cy, so there's one known, two unknowns. We have our Cy, which we calculated to be 3.125 kilonewtons. You have your FCD coming down. This is a 345 slope triangle. And you have your FCB. So two unknowns, one known. If I take my sum of my forces in the y direction, I have my Cy, which is 3.125 kilonewtons, minus FCD times 3/5. You get FCD. And FCD is compressing at joint C. So then I'm going to take my sum of my forces in the x direction. You have your FCD, which we know now is 5.21 kilonewtons, times the x component, 4/5, minus FCB. FCB is 4.17 kilonewtons, and that's in tension. So now we know the force in members CD and BC. All right, so now if we go through joint, say, A next, we know AX and AY. Remember, AX equals to 3 kilonewtons. AY is 0.875 kilonewtons. So we have two knowns, AX and AY, and two unknowns, AD member and AB. So FAD and now FAB. Two knowns, two unknowns, we can work it. So I take the sum of my forces in the y direction. We have 0.875 kilonewtons, which is my AY, minus FAD times 3/5 FAD, 1.46 kilonewtons, and is in compression. Take the sum of my forces in the x direction. You have your unknown FAB minus your AX, which is 3 kilonewtons, minus your FAD, which we now know is 1.46 kilonewtons, times the x component, which is 4/5. Solve for AB. You get FAB is, and AB is in tension. Last but not least, if we go to joint B, FBD, which is an unknown, we know the 4 kilonewton force here. We calculated FCB previously. To be 4.17 kilonewtons. We just calculated FAB to be 4.17, which checks out good. So the last remaining unknown member, FBD, so I'll take the sum of my forces in the y direction and set it equals 0. I have FBD minus the 4 kilonewtons FBD is 4 kilonewtons and is in tension. So we've solved for all the members and the forces. All the forces in the members, I'm sorry. Take a look at another problem. Problem 511 on page 238. Once again, determine the force in each member of this truss. State if the members are in tension or compression. Set P equals 8 kilonewtons. Joint C, joint D. This is a rocker at E. A is a pin. B, I believe that's everything. Okay, so if I start at joint D, we have one known, the 8 kilonewton force, two unknowns, forces in members CD and ED. All right, so at joint D, we have the 8 kilonewton force coming down, FDE, and we have FDC. Two unknowns, one known, and this angle is given to us at 60 degrees. So I'll take the sum of my forces in the y direction. I have FDC times sine of 60 minus 8 kilonewtons. You get FDC is 9.24 kilonewtons, and it's pulling, so it's in tension. Take the sum of my forces in the x direction. I have FDE minus FDC, which is 9.24 kilonewtons, times cosine of 60 degrees to get the x component of FDC. FDE is 4.62 kilonewtons, and it's compression. So if I now go to joint C, we know CD, FCD, which is calculated at. So joint C then would have, we have FBC, which is unknown, FCE, which is unknown, have, FDC, which we calculated previously as 9.24, this angle between the horizontal, this angle is 60 degrees. So working at joint C, one known, 2 unknowns. Take the sum of forces in the y direction. You have FCE times sine of 60 minus FDC, which we know, 9.24 kilonewtons times sine of 60. FCE is 9.24 kilonewtons. And that's in compression. Take the sum of my forces in the x direction. We now know FCE. So it's 9.24 kilonewtons times cosine 60 degrees plus 9.24 kilonewtons times cosine of 60 degrees as our FDC minus FBC. FBC is 9.24 kilonewtons. And that's pulling, so it's tension. So we go to joint B now. We know FBC, which we just calculated to be 9.24 kilonewtons. We have our FBE, which is unknown, and our FAB, which is unknown. This angle is 60 degrees. This angle is 60 degrees. So we have one known, 2 unknowns we can solve. Sum of forces in the y direction. You have FBE times sine of 60 degrees minus FAB times sine of 60 degrees equals 0. So therefore, FBE equals FBA. Take the sum of my forces in the x direction. You have your FBC, which is 9.24 kilonewtons, minus, and we'll say FBE equals FBA, so we can, substitute either one. So in the x direction, we have the 9.24 in the positive x direction, minus your FAB in the negative x direction, and we need cosine, minus your FBE So solving these two equations, either by substituting, you get FAB equals FBE, they're equals to 9.24 kilonewtons. And FBE is in compression, FAB is in tension. So last but not least, if we go to joint E, we've determined FDC, we've calculated FDE, so we got FDC, FDE, we got FCE, FCB, we got FBE, and FBA. So last but not least, we need FEA. So if we go to joint E, remember the rocker, so it's a EY component. We have FDE, which we calculated to be 4.62 kilonewtons. We have a FCE, which we calculated to be 9.24 kilonewtons. We have a FBE, which we just calculated to be 9.24 kilonewtons. And we have a FAE, which is our last unknown member force. So if I take some of our forces in the x direction equals 0, you have your FAE minus your FDE, which is the 4.62 kilonewtons, minus your FCE, which is your 9.24, but we need cosine of that 60-degree angle, minus your plus your FBE, which is your 9.24 kilonewtons, once again, times cosine of 60 degrees, equals 0. Solve for FAE. You get FAE equals 4.62 kilonewtons as in compression. Okay, we'll stop here for today's lecture. If there are any questions, please do not hesitate to send me an email. Have a safe day.